Start. Hello everybody. Today we come to our fourth lecture on graphs and we cover a very important topic called the minimum spanning tree or the minimum cost spanning tree of a graph. The spanning trees are defined over undirected graphs and minimum cost spanning trees are defined over weighted undirected graphs. But before we come to the minimum cost spanning tree, let us come to the definition of a spanning tree. Given a graph, and let us assume that this graph is connected, that means there is a path from every vertex to every other vertex through the edges. A spanning tree of the graph G consisting of nodes V and E is a subgraph of G which contains all the nodes of G, but it also is a tree and it is connected. So there are these three properties. A spanning tree is a connected subtree of G covering every node. That means that every node in G is covered by a spanning tree. Let us look at this example of figure 1. Let us see how we can form a spanning tree. Let us choose this edge. Let us choose this edge, 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 and let us choose this edge. If we choose the red colored marked edges, then we get a tree, which means that there is no cycle in this red colored marked edge. And does it cover all the nodes? No, it still does not cover node 1. So we have to add either this edge or this edge. And suppose if we add this edge, then we have these 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 edges. 1, 2, 3, 4, 5, 6, 7, 8. We have these. So as we see from the red colored edges that we have here, there are 9 nodes in this graph 0 to 8 and there are 8 edges which form the tree of the spanning tree. Therefore, by definition, a spanning tree, as is written here, consists of all the V vertices of G and the set of edges E dashed in the spanning tree is a subset of the original set of edges in the graph, such that by the spanning tree the graph still remains connected by the edges of the spanning tree. Thus, if there are V vertices in the graph, then there will be V minus 1 edges in the spanning tree. It is not difficult to prove that there will be V minus 1 edges and V vertices in the spanning tree of this graph. There is another very interesting property which we shall see later on, is that this spanning tree may not be unique. There can be many spanning trees of the same graph. For example, if we look at the same graph, we can draw a spanning tree by including this edge, 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 and this edge. Here again we have 1, 2, 3, 4, 5, 6, 7, 8 edges and it's a different spanning tree. If we do a DFS traversal, which we shall see later on, the tree edges of any DFS traversal will also give us a spanning tree of the graph. Now let us consider this figure, figure 2. Whereas if this figure is figure 1, then this figure is figure 2, then this figure is a graph which is disconnected and we have seen this graph before. And we know that there are 4 components of the graph. Therefore, a spanning tree will be there for each component. And in this one, for example, in this one, this could be a spanning tree for this subgraph. This is a spanning tree for this graph. This is a spanning tree for this subgraph, and this is a singleton node which is itself a spanning tree. Therefore, we will have as many spanning trees as many connected components are there, and together they form what is called a spanning forest. Let us quickly revise how our depth first search will work. We remembered in the depth first search, we had a visited node, we had a parent of a node. A parent of a node was created when a new node was visited. Therefore, we marked the parent node. We had the successor set of nodes. Now we define the tree edge. The tree edge is defined as soon as a new node is visited. That is why in the beginning in DFS we mark a node to be visited. For each successor which is not already visited, we mark the parent, and here is where we mark the tree node. And then we recurse. So if we start from node 0, then node 0 is visited. The next node, there are three successors. The next node that we visit is node 1. We mark this one as the parent, and we mark this edge as the tree edge. So we mark node 0, 1 as a tree edge. Next from here, we mark this node as visited. This is the parent, and this becomes the tree edge. Similarly, from here, this node becomes visited. This is the parent, and this is the tree edge. From here, this node becomes visited. This is the parent, and this is the tree edge. From here, this node is already visited. There is nothing to do. Then this node becomes visited. This is the parent, and this becomes the tree edge. From here again we have to go to this node, then this node, this becomes the parent, this becomes the tree edge. Then we backtrack out because nothing else can be done. We go back to 2, then we go to 5, this becomes the parent, and this becomes the tree edge. From 5 we go to 6, and in 6 this is visited, this becomes the tree edge, and this becomes the parent. And you can see we have 1, 2, 3, 4, 5, 6, 7, 8 edges which are formed out of this. So by a basic DFS search, a spanning tree can be formed. By BFS also a spanning tree can be formed, and I leave that to you as an exercise. Now we come to the main topic. Now we have got a weighted undirected graph, which means that there are weights on the graph. And therefore, what we are looking to find is what is the minimum cost spanning tree. Now, given any spanning tree of a graph, the sum of the edge weights of that spanning tree makes the cost of the spanning tree. And we are now looking for that spanning tree of the graph whose cost is minimum. So here, given a connected weighted undirected graph GVE, a minimum spanning tree is a spanning tree of G of minimum cost, where cost is equal to sum of edges of the tree. As we have said, there may be multiple minimum spanning trees also, but all of them will have the same identical cost. There's a very interesting property. The interesting property is that if the edge weights of a graph are unique, then the spanning tree, minimum cost spanning tree, is also unique. Let us see the example of figure 1. In figure 1, we do not have unique edge costs because we have several costs which are there. This cost is 9 and this cost is also 9. But this cost, spanning tree of cost 33 that is shown in this figure, this is a minimum cost spanning tree of the graph. The minimum cost spanning tree contains all the nodes of the graph, so it is a spanning tree. It contains exactly n minus 1 edges where there are n vertices of the graph. But the cost here, which is 33, is actually the minimum cost. On the other hand, If we go to this one, this example, you will notice in the example of figure 2, while there are 8 nodes, each edge cost is unique. And since each edge cost is unique, we can now form a unique minimum cost spanning tree of the graph, which will consist of the following edges. How we determine it algorithmically, we shall see later on. But now I am just showing you what are the edges of the minimum cost spanning tree of this graph. And those who are observant will be able to see later on how an algorithm can be formed out of these. So all the nodes are covered by these red colored edges. There are 1, 2, 3, 4, 5, 6, 7 edges covering all the nodes, and the sum of these edges is the unique minimum cost spanning tree of this graph. The minimum cost spanning tree has got a number of applications. For example, consider these nodes, these 8 nodes of figure 2, to be the nodes where some connection is to be made so that information can be passed in a network. Say it's a telecom network. And if it's a telecom or a broadcast network, we want to find the minimum number of connections so that everybody can send messages to everybody else. And assume that the edge weight is the cost of forming these connections. Therefore, the minimum cost spanning tree provides the minimum cost mechanism to lay out a network connection between these 8 nodes so that everybody can communicate with everybody else. In a similar manner, people form transport networks, water supply networks, power grid networks. In a circuit, let us say, if there are 3 nodes in a circuit and they have to be connected to each other, and there are various ways in which you can connect them pairwise, then we would look only for 2 connections between them so that we can connect. And so the whole area of network layout, whether it's circuits, whether it's telecom, whether it's transport, water supply, power grid, any sort of connectivity, where we are looking to connect everybody to everybody else with minimum cost, leads to the spanning tree problem. In geometry, in vision, in image processing problems, we have a problem called the visibility problem, which means that people there is a line of sight between 2 entities, and you can draw a graph with this line of sight. And the way you draw the graph is all the nodes that need to be seen between each other are the nodes of the graph. Between 2 nodes of a graph, there is a connection which forms the connectivity or line of sight. If there is no line of sight between them, then therefore there is no connection between them. And if we draw this whole visibility graph between pair of nodes, and if we want to put a minimum number of observers, that means we have to find those nodes so that the cost of observation could actually be the edge cost. And therefore the total cost of observation can be minimized by finding the minimum spanning tree. There are several other problems in image processing, segmentation, handwriting recognition. There are many problems in physics, etc. Many hard problems, which we shall see later, like the traveling salesman problem, the Steiner tree problem, require an approximate solution. Hard problems are those for which till now there is no known fast polynomial time algorithm. The spanning tree provides an approximation to quickly find a quick bound to these very hard approximation problems. The spanning tree is also used in various physics problems. Spanning tree is also used in various cosmology problems. A spanning tree is used in various chemical binding problems, and so on and so forth. It is a very popular problem and has got widespread applications, and as we shall see later on, has got some very wonderful algorithms. Now let us use our method of trying to find out by initially developing a recursive definition for the problem, then analyzing this recursive definition, and then from the recursive definition, we have our various options. One option we have is memoizing or dynamic programming. One option we have is balancing the recursion. The third option we have is greedy choice of the recursion. And the fourth option we have is branch and bound. We have discussed this in details earlier. Now we will apply it. What we do is as follows. We consider at any point in time that the algorithm has got two graphs, subgraphs, G1 and G2. For G1, the MST for all the nodes in G1 are already found. G1 union G2, G is equal to G1 union G2. So we now assume that for G1, all the nodes of the minimum spanning tree are found for the nodes in G1, and we selectively start choosing nodes from G2 so that we are able to form the minimum cost spanning tree. So our algorithm proceeds with G1 as one argument, G2 as the second argument, and T as the MST of G1, which is already formed till now. So what we now do is our base condition, this is our base condition in blue. Our base condition says that if G2 is null, which means that all the nodes are now of originally G are in G1, then all we have to do is return the tree T, and the remaining cost that comes from G2 is 0. So this is the base condition. Otherwise, this is the most important condition. What we now have, let us assume, we have a few edges going from G1 and G2. So each edge, let us say, is E1, E2, E3, and it occupies some node here. Now we branch out in as many ways as there is these number of edges. What we do, suppose we choose E3, then in G1, we add G1 plus E3. In G2, we remove E3 from G2. So we put E3, therefore suppose this node is N1, this node is N2, this node is N3. So now this node N3 will now go back into G1. So if we add here, which means we are adding the node N3 and we are removing the node N3 from here, and we are adding this edge here. And from these two parts, we recurse and again find the rest of it by reducing G2. So that's what we do. What we do is, for each edge, so let me use the highlighting pen a little. And so what we do is, for each edge E from G1 to G3, as we have seen here, from G1 to G2, recursively find the minimum cost tree cost A using the remaining part of G2 and the corresponding tree T. So what we do, as we have just said, if the edge E consists of is NM, then we add NM to G1. We add M to G1. We remove M from G2. We add the edge E to T, and we recursively call it on G1A, G2A, and TA. And whatever we get back is a tree T dashed and a cost dashed. The tree T dashed is the minimum cost tree that we get back. by including the tree that was already in G1, and we add this edge cost to the cost that is returned and form cost A. Now, among all these edges E1, E2, E3 that comes out, among all the values that are returned, we choose the minimum. And that minimum is the return from here. So if T min is the minimum of all the T dashes, if cost min is the minimum of all the costs of each edge, then that cost min is the minimum cost we return out of this as it goes back. So what we have done is we have chosen each and every edge and done a recursion. And how do we start? We start with any node as one single node of G1. Let us see how it works on this example that we have. Let us say we initially start with this as G1. Then we have got two nodes, one node going out this side and one node going out this side. So we recurse in two branches as mentioned here. What we do is, in one case, we choose this as G1 and this as G2 and go to the recursion. In the other case, we choose this as G1 and this as G2 and go to the recursion. And from these two cases, the blue case and the green case, whatever is returned, we add this to the one which is returned from the blue side. We add this edge to one which is all returned from the green side. And among these two which are returned, whichever is the smallest, is now returned from here. This is how the recursion proceeds. Now we shall see what happens as we go ahead. Let us take another example of how the algorithm will proceed. Let us revisit the algorithm. The algorithm has got G1, starts with G1 and G2, and we initially call it, let us say here in this case, let us say we call it with MST E and G minus, and the tree that we call it with is just containing the node E and no edges. This is how it is called. Once it is called this way, then we know what is the recursive base condition if G2 is null, but in this case G2 will not be null. So let us assume that we start with this node E. We have started with this node E and we have got three edges. Edge moving out 11, edge moving out 3, edge moving out 4. Suppose we choose the edge moving out 4. Then what we have chosen in one case will be, this will become G1 and this will become G2, and we will recurse. This will become G1, this will become G2, and we will recurse. On the other hand, if we chose edge this one, then this would become G1 and G2 would be this plus this. On the other hand, if we chose, let us say, E and F, then this part would become G1 and all the rest would become G2. We would recursively call it on these three parts. Whatever comes back from each of them, in one we would add the cost of 4, in the other we would add the cost of 3, in the third we would add the cost of 11, and then after adding these costs, we would get these costs, cost A of each of them. In one case, we would add 3, 4. In another case, we would add 3. In another case, we would add 11. And out of these three cost A's that we get from the three recursions, whichever is minimum, that will be cost min, and that graph will be T min, and that will be returned. It is easy to prove by induction. So it is a proof by induction. A proof by induction. It's straightforward for us to see that if G1 at any point in time is the minimum cost spanning tree, and we have seen all the other edges that come out of G1 and take the minimum out of whatever is returned, then we can guarantee that whatever we have added into the whole result will also be a minimum cost spanning tree. Just in case we want to go into more details, then here is the case. If we have chosen this one, suppose we chose this edge, then we branch in this direction, and we have done this case and this case. Now, from here, how would we go? From here, we have got again three options. If we chose this option, we could choose this option, or we could choose this option. It is easy to see that this option and this option leads to the same node, and therefore we can very quickly observe that this one, which is of cost 3, is definitely better to take than this one, which is of cost 5. This observation that here from these three we can actually delete one of them will lead us to a more detailed observation that we shall see later. Therefore, from here, the recursion can break down into two parts. One, which has now chosen, so this was chosen. Now, we will choose from here. One option is to choose this one, which means I have now this as, so from here I have moved here, from here I have moved here. This would be this graph. I have another option to go from here is I've chosen this and I've chosen this and this and this would be coming here. Let us say we want to go down again from here. From here we have got, so if we have got these three nodes in G1, then we have one edge coming out of here, one edge coming out of here, one edge coming out. And therefore, for these three edges, of which this and this goes to the same node, we might as well just choose one of them. Therefore, we have got this option, this option, this option, three options, sorry. We have got an option of 11, we have got an option of 12, from here. Now we have moved from here to here, and therefore, from here, we will now move to either this node with this edge, or this node with this edge, or this node with this edge, or this node with this edge. Therefore, there will be three branchings, one going to node F, one going to node G, and one going to node C. Suppose we chose this one. Then our G1 will become like this, and G2 will become like this. Similarly, from here, we could choose node D, and we would reach something like this, and G2 would remain like this. From here, we could go to this node, and from here we could choose node H, and this would remain like this, and G1 would be like this. From here, from node H, we could choose node G, and this would remain like this, and the rest of it would become G1. And it is at this point that F would be chosen, and we would get a null situation, and then backtrack And obviously we would have to see all the options. And by seeing all the options, we are guaranteed to see how this algorithm will work. If you open up the recursion, let us see how do we analyze the properties. As we have seen in the example before, if you open up the recursion, then you will get a large number of options and you will get a lot of identical options. But if we analyze the properties very carefully, then we will see that there are certain very interesting observations that we can make. And the first observation that we make is as follows. Suppose we have started from here. This is G1 and this is G2. If this is G1 and this is G2, then there are three edges coming out. Edge cost 4, edge cost 3 and edge cost 11. They're going to three different nodes. Now I make a claim. I say that if I choose only the one with among these three, the one which I choose, if I choose this as the one which is minimum, and I just choose this one directly, and I will try to prove that this edge will be in the minimum cost spanning tree. That is, among all the nodes that come out from this side to this side, this edge will be guaranteed to be in the minimal cost spanning tree. The question is why? The question is, if E is here and the rest of the nodes are here, I had a cost 11 coming out, I had a cost 3 coming out, I had a cost 4 coming out. Now let us say that I have got the MST of G2. Now if I have already got the MST of G2, then getting the MST of G by connecting E, if I connect it with anything other than 3, I will get a larger cost. Which means that by recursion, since I am getting the MST of G2 out here and putting it back, it is obvious that the only and the best and the minimum way to connect E with the rest of G2 is by connecting this node 3. Which means that from all the possible edges, we saw two examples earlier where two edges were going to the same node in G2. And we saw that from the two edges which were going to the same node in G2, we could choose the one which is smaller. Now we are making a much stronger step. Now we are saying that among all the edges that can go from one side to the other, the minimum cost edge is enough to be chosen, and that will guarantee the minimum cost spanning tree. So what are we saying? We are saying that if G1 and G2 are the two sets, for G1 we have proved that we have already got the minimum cost spanning tree till now. So for G1 MST, it is the minimum cost spanning tree. In G1, whatever we have got in T till now, is the minimum cost spanning tree. T is the MST of G1. G2 is the remaining set of nodes. And there are, let us say, three edges, E1, E2 and E3, coming out from G1 to G2. Let T dashed be the, let T dashed be the MST of, let T2 be the MST of G2. The T2, which is the MST of G2, will connect all the nodes of G2. Therefore, the MST of G1 and G2 will be the T connected with T2 by some edge. Which edge will I connect this side from all the possible edges? I will obviously, because they are two disjoint set of vertices, I will obviously connect it by the one which is of minimum edge. Which means that now, suppose E2 is the minimum edge. Suppose E1 is 5, E2 is 1, and E3 is 12. Then obviously I will connect it by 1, because if I connect it by any other combination, I will get a larger spanning tree. So by this we see that from all the other options, we are now able to reduce our recursion and get to a greedy choice. So how does the algorithm pan out? The base condition remains the same. All we are saying that from all the edges from G1 to G2, this part is not there, find the minimum cost edge E dashed from G1 to G2 and just include that in G1, remove that from G2, do that edge and recursively call it this way. And there's only one cost that you will get back, and that cost is to be returned. Which means that of all the branchings, we have been able to now actually reduce to a single branch. So we have seen that we are able to make a greedy choice and come to the final algorithm. Let us do another example. In order to do another example, so what we will do, let us say we start from node this way. If we start from node 0, then there are two edges going out. So we choose the smaller edge. Once we have chosen the smaller edge, then this becomes part of G1. This 0 was in G1, now this is in G1. Now there are three edges coming out from G1 to G2. There are two of cost 8 and one of cost 11. We can choose any one of these two. Let us say we choose this one. We choose this one and then we choose this edge. Then we have now 1, 2, 3, 4, 5 edges coming out from G1, of which we can see this one is the minimum cost edge. So we choose this one. From choosing this one, we have got 1, 2, 3, 4, 5, 6 edges coming out, of which the minimum cost choice edge is this one, which is of cost 4. Now from this, we can easily see that the next minimum cost edge is this one. The next minimum cost edge to be chosen is this one. The next minimum cost edge to be chosen will be from 7, 14 and 10, which therefore will be this one. The next minimum cost edge chosen will be between 9, 10 and 14, and therefore will be this one. And therefore all the edges marked in blue will give me the minimum cost spanning tree. That means that the algorithm can now move in a greedy fashion. So just let me repeat the algorithm. At any point in time, among all the edges that are coming out, choose if this one is E1, this one is E2, this one is E3, choose the one with minimum cost and recurse. So we have now seen this example. Let us now do an analysis of this algorithm. What is the analysis of the algorithm? The algorithm at any point in time has to do the following. It has to find the minimum edge. Once it has found the minimum edge, as soon as it includes all the other, one node from this to other and recurses, it has to add edges. So what if we create a min heap of edges? Then we have to insert edges and delete the minimum cost edge. And each edge will be inserted only once because it is an edge from one side to another. And we have to find at most v minus 1 number of minimum calls on the heap, because we have to choose, if there are v vertices in the original graph G, we have to choose only one less than that. Therefore, if we have to choose all the edges once and we have to do a min heap, then the algorithm is of the order of E log E, where E is the number of edges and E is the same as V. Log E can at most be V squared, and log of V squared is 2 log V. So this actually turns out to be an order E log V. This is the simplest way to implement this algorithm. There are better ways to implement this algorithm by using more complicated data structures like Fibonacci heaps, which will reduce it to V log V, but I leave that for you to examine. There is this algorithm that we just discussed. This algorithm that we just discussed is popularly known as Prim's algorithm. Though Prim was not the first to find out this algorithm. This algorithm was found out at least 20-30 years before Prim by other people. But in the literature today, it is very famously known as Prim's algorithm. There is another algorithm which goes by the name of Kruskal's algorithm. This algorithm has got a slightly different mechanism of operation. It is a recursive algorithm, but I am not showing it from the recursive point of view. What it does is as follows. The simple mechanism is it sorts all the edges. Then it picks up one edge at a time. From the sorted edges, the edges are sorted in increasing cost. It picks up one edge at a time, and every edge that it chooses, it checks whether it forms a cycle. So every edge that it chooses becomes part of the minimum spanning tree, and as soon as it chooses an edge, it checks whether the new edge that is chosen forms a cycle in the already partly formed minimum spanning tree. If it is already there in the partly formed minimum spanning tree, then it rejects that edge and goes to the next one. So this it continues till either all the edges are exhausted or at least V minus 1 edges are chosen, which means the spanning tree is formed. So let us first look at the example, then we'll go to the algorithm. So here is the algorithm. So initially, let this be the tree. Then, if this is the case, then this is the minimum cost edge. So this is chosen. From here, the next minimum cost edge is 2. So from here, 1 is chosen and then 2 is chosen. Please note that unlike the Prim's algorithm, this does not form a tree, but it just connects edges to form a forest and slowly it will get connected. From here we see that the rest of the edges are of course 3, 4, 5, 6 and 7, and obviously 3 is the minimum. So this is chosen, this is chosen, and this is chosen. Now we see the minimum cost edges are 4, 5, 6 and 7, but if we choose 4, then we are in trouble, because if we choose 4, then our problem is that a cycle will be formed. Now since a cycle will be formed if we choose 4, we are not going to choose 4. So we'll discard 4. And after discarding 4, we will choose 5. So this. Now it covers all the edges. So as I said, the algorithm proceeds by sorting the edges. And after you sort the edges, you start choosing the edges one by one and reject only that edge which forms a cycle in the already chosen subgraph. So the algorithm pseudocode is as follows. Sort the edges in terms of cost. Initialize VT, which is the minimum spanning tree graph to be formed. Initialize ET to be null and cost to be 0. While the edge set, which is already sorted, is not empty, or we have chosen all the vertices of the graph, choose the next minimum edge cost in E. Let it be NM. Add it to E. If adding NM in E makes a cycle discarding, so rather we could do, instead of adding it here, we could discard E and we could add it here. So what we could do is we could add it E. Yeah, this is fine because we are removing E from the original edge. So let that be here. We are removing E from the original edge. If adding N, M in VT make discard E, otherwise we add the node M and N, and one of them could already have been in the VT, but we just add them now. If none of them are there, both will be added. If one of them is there, one will be added. We add this edge back to ET, we add the cost. And we go on doing this as we have seen in this example. So we go back to our other case and see how the algorithm works. In this case, the first edge that will be chosen is edge cost 1. Then this vertex is chosen, this vertex is chosen. The next edge that will be chosen is edge cost 2. This vertex is chosen, this vertex is chosen. So now, because this vertex was already there, in both of them, only one of them will be added. The next is again of cost 2, and these two are chosen. The next that we get is of minimum cost 4. So this will be chosen, and these two will be chosen. The next one is also of cost 4, but if I choose this, do I make a cycle? No, because there is no cycle. So I'll choose this edge. And if I have chosen this edge, I have actually not made any cycle, but I have connected two disjoint subtrees, if you have noticed. This was a disjoint subtree, this was a disjoint subtree, I have connected these two. Now the next minimum cost edge is of cost 7. So I could choose this one, but if I choose this one, then I will form a cycle like this. So I cannot choose this edge. This edge cannot be chosen. This edge is discarded. Now I choose this edge. The next edge that could be chosen is 8. But if I choose this edge, do I form a cycle? No. But this, if I do this, then this connects this subtree with this subtree. So I connect this. And notice that no edges are added. This is just a union operation. The next edge to be added is again 8. If I add this, then I will form a cycle. So I cannot add this edge. The next edge to be chosen is 9. And once I have chosen this, you can figure out that I have chosen all the vertices of the graph. So this is how I implement Kruskal's algorithm. Again to repeat, while initially I sort all the edges, while E is not empty, I choose the next minimum edge. I remove that from the original set of edges, and I check whether a cycle is formed. If a cycle is formed, I discard E. If a cycle is not formed, I include the edges if they are not already included. I include the vertices if they are not already included. I include the edge and I add the cost. And at the end, I return the total cost. So how do we analyze this algorithm? There is a sorting complexity, which we all know will be order E log E, which is the same as order E log V, as just mentioned earlier. Then we have a very tricky thing to do is cycle detection, which means, as we have seen earlier, that by adding an edge, we may add a new edge, which is a new node, but we may also connect to existing node. There are three cases. By adding a new edge, both the nodes n and m may be new, one of the nodes may be new, or none of the nodes may be new. If both the nodes are new, we don't have any problem. There is no chance of any other detection. If one of the nodes is new, again, we are just adding to an existing part of the component. But if both the nodes are already existing, there are two cases that are possible. One is a cycle, which we will have to detect. The other is that two trees get joined. So now we have to run what are called determination of cycle. Now, checking for this cycle detection is not a straightforward issue. If you notice, what we are trying to do here is we are forming disjointed sets, and by an edge, initially all the sets are the singleton nodes, and by every edge we are merging two sets into one set. Now these sets, for example, as soon as initially all the nodes are disjoint sets, as soon as I connected these two, this became one set. Again, when I connected this and this, these two became the same set. Then when I connected this and this, these two became the same set. So that's what I'm doing, is I am actually forming operations of union of sets. And if I really do connect two nodes which are already in the same set, then I know that there is a cycle formed. If I connect two nodes in different sets, a cycle is not formed. So this cycle detection can be done by forming a data structure which maintains the set of nodes, and as soon as two nodes are joined, then we will have to merge these two set of nodes into a single node. And our cycle detection algorithm will find out that if the sets which are connected by this new edge are the same set, then there is a cycle. Therefore, in order to implement that efficiently, we have a famous data structure called the disjoint union find of sets, because these are all disjoint union and find. Normally in sets, the intersection of sets may be common, but here the sets have got no intersection which are common. So we rewrite the Kruskal's algorithm with the set operations of the disjoint union sets. So initially our algorithm is, our chosen elements are A, which is null. For every vertex, we make a set consisting of that singleton vertex. Now again, the edges are all sorted. So we choose an edge ordered by increasing weight. We choose the next edge after sorting. And we check for cycle. This is the cycle detection. If the edge connects the same set, so we find the set in which U exists, we find the set in which V exists, and if they are same, then there is a cycle. So if they are not the same, then we add this edge to the minimum cost spanning tree, and we do a disjoint union of these two sets. And this union is a disjoint union. That means we are connecting two sets which are disjoint. There are very efficient algorithms for operations on disjoint sets. This will be covered in a separate section. And as we will be able to see that by using these disjoint union find operations, we can also do the Kruskal's algorithm in order E log V time. And there will be more efficient algorithms which could do it in order V log V time. But the disjoint union find is a famous algorithm. So today we have just covered the spanning tree of a graph, the minimum cost spanning tree of a graph, and we have done two algorithms, one which we call the Prim's algorithm, the other which we call Kruskal's algorithm. And in the Prince algorithm, we followed our algorithm design approach of developing an initial solution. Then we went on to refining that solution, analyzing its properties, choosing a greedy approach, then choosing a min heap data structure which would memorize all the nodes that are there and getting an efficient algorithm. Similarly, we found that we have the Kruskal's algorithm from where again we had to develop a new data structure which is called the disjoint median. Thank you very much. Please get back to us if you have any questions.